Last class we derived some very important relations using Bohr's theory. We derived a formula or a relation, okay, rather it's a relation for radius, speed and energy. Radius, speed and energy. Okay. Then we are going to solve a few problems here. I'm sure that you must have solved a few problems from the sheet. That is very much required. After every lecture, you have to solve the problems from the sheet. Okay. Now, all of these problems, just remember few basic things. Only few basic things you have to remember. Okay. And you are going to solve every problem from this chapter. Every problem. The chapter itself is very simple chapter. Okay. And if you do it a little carefully, you are going to solve every problem in examination which are based on this chapter. Just remember few things. For example, the first thing, I'm just writing down few equations, and if you keep in mind only those equations, okay, you are going to find solve every problem, okay, using one or the other equation or all of them, okay, in a given problem. The first one is quantization of angular momentum, MVR is NH over 2 pi. MVR is NH over 2 pi. Okay, what is this? This is quantization of angular momentum. This is angular momentum of an electron in an orbit of radius r moving with this speed v. It is angular momentum. It is going to be integral multiple of nh over 2 pi. N is the state. It starts from 1, 2, 3, 4. It's like orbit. Its states are orbit. Okay. So first state is the first orbit. That is the closest orbit. Okay. So I have this nucleus here. It is a positively charged nucleus. And this is the closest, the first orbit, okay, of the minimum radius. This is the first state also. N is equal to 1. Then the second state, then the third state, then the fourth state. Okay. How many states we have, by the way? How many states we have? Infinite. Infinite states. Infinite possibility. Okay. Infinite. Okay. Then this is also the first orbit, also known as the first state. This is about orbits and states. Okay. Now the second one is that we have to remember. Okay. Of course, it's always better if you can keep in mind all those relations. Okay. But few are like essential, fundamental, okay, mandatory. You have to remember them. The first one is this. The second one is this. This is energy. It is minus of 13.6 and then Z square over N square, and this is in electron volt. Z is atomic number. N is the orbit. Okay, first orbit, second orbit, third orbit, or state. First state, second state, third state. Okay, all right. Then energy is equal to minus of K. What is K? K is kinetic energy. Okay, and potential energy is equal to minus 2K. Minus 2K. Potential. Now, but I remember this equation. I am not remembering the equation for kinetic energy. I have to memorize this relation for the total energy in any orbit, minus 13.6 and this. This includes both kinetic plus potential. Potential of the atom. Okay. Electron plus nucleus, both. Potential energy. Okay. Now, generally we remember this. Okay. So it's better if I write the kinetic energy in terms of this. So I can write kinetic energy as minus E. Minus of E. Okay. And then I can write potential energy. Potential energy will be equal to, from here itself, I can write it as 2 times of E. It is 2 times of E. Okay, 2 times of E. Potential energy is double of total. Okay, a part of something is double of the whole. A part of something is double of the whole. Okay, well, try to make sense out of this. It's because of these negative numbers, that's why. If you remember only these things, you are going to solve problems. Okay, or if some other problems are asked which cannot be solved using these equations, then what we do? Then we remember the basic derivation, the derivation that we did in the last lecture. For example, this last problem here, this last problem cannot be solved using these equations. You will have to derive those equations, okay, from the basic that we did in the last lecture. Okay, so now let's start doing the problems. Okay, the first problem is very simple. I just have to write energy, all types of energy in different orbits, 1, 2, 3, 4. Okay, let's write it. Energy, kinetic energy, total, potential and all that. Okay, let's see. Let's start with writing the total energy first because it's simple to write. Because I have remembered it. It is minus 13.6 Z square over N square. This is in electron volt. Now, this is my nucleus here. Nucleus. This is first orbit. First orbit. Okay, then second, then third, and then fourth here. Okay, this is N is 1, state 1, state 2, state 3, and this is state 4. Now let's write the energy. What will be energy? What do you think? Energy here, E1. Okay, Z is 1. We are doing it for hydrogen atom. Okay, we are doing this for hydrogen atom. So this Z is 1. Okay. So 1, N is 1, it becomes minus 13.6 electron volt. Okay. Now here, second state, E2. What will be E2? E2 is minus 13.6 over 4. N square is 4, okay. So this becomes minus 3.4, minus 3.4 electron volt. Okay. E3. What will be E3? Minus of 13.6 over 9. Okay. This will be approximately minus of 1.5 electron volt. Okay. And then this fourth one here, E4. E4 is equal to minus of 13.6 over 16. This will be approximately 0.85 electron volt. Okay. Do I need to remember these? Do I need to remember these values? Okay, no, of course no. Okay. Obviously I don't have to remember it. I just have to remember this formula, that's it. Okay, only this formula. Formula I need to remember, undoubtedly. Out of these states, or if you can calculate it for 5th, 6th, 7th, 8th, any number of states, there are infinite possibilities. Energy of which state is minimum out of all these? Taking into consideration the negative sign, energy of which state is minimum. This is the minimum energy. Okay. Here, energy of this state corresponding to the first orbit, N is equal to 1, first state. The energy here is minimum. This is known as ground state. This is known as ground state. Ground state. And all others are known as excited states. The ground state is the state in which energy is minimum. The atom is in a state of its minimum energy. It is known as ground state. Ground state. Okay. So if I have an atom, a relaxed atom, okay, there is no excitation, nothing at all. In that case, in which state? It's a hydrogen-like atom. hydrogen-like atom, that means single electron system, only one electron. In which state the electron will be found? Every system in nature tries to find stability. Understand this, try to correlate stability with energy. More the energy, less is the stability. Energy increases, stability decreases. Lower the energy, higher the stability. Every system in nature, every system, whether it is a single molecule, a single atom, or a bulk, or any object, or any system, every system tries to minimize its energy. Okay, so the electron will be found in n is equal to 1, the closest orbit here, that is its home. That's where he finds relaxed. He finds, okay. So this is known as ground state. In all other states, energy increases. All of these are excited state. Okay. Now the first one here, n is equal to 2. You see, this becomes a ground state. This is ground state, and this is all the others are excited states. Okay. So this out of all the excited states, this is the first one. It is known as first excited state. First excited state. Okay, this is second excited state. Second excited state. Okay, similarly, this is the third excited state. Okay. Be careful about the nomenclature. Problems are asked like what is the energy of hydrogen atom in second excited state, in sixth excited state. Okay, so you have to carefully look at this nomenclature. Okay, I hope I don't have to explain too much. Now, so ground state and excited state. Okay, for example, here the problem is asked like this. Here, you see, in case of helium plus ion, how much energy is required to move an electron from ground to second excited state? So you should know. Second excited state corresponds to which state? 1, 2, 3, 4, 5, which one? Okay, like that. So this is our total energy. Now we have to write kinetic and potential also. Okay, so let me do this again. Okay, let me write it here. Okay, it's like this. This is my it's like this. This is n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. This is total energy. It is minus of 13.6 electron volt. This is minus of 3.4 electron volt, minus of 1.5 electron volt, minus of 0.85 electron volt. Total energy. Now, if I use this relation here, that K is equal to minus of E, and U is equal to double of E here, 2E. Remember this relation, it's very, very important relation. So what will be kinetic energy? It's just positive of this, plus 13.6 electron volt, okay, plus 3.4 electron volt. Keep in mind, kinetic energy is always going to be positive, always, in all the cases, okay. This is plus 1.5 electron volt, and here it is plus 0.85 electron volt. Okay, now what about potential? I can write like this: E is K plus Q. This tells me U is E minus K. E minus K. Either you apply this minus this, it will simply become double of that. Okay, you will realize that. Or you can directly apply this one here. U is 2E. So it is simply double of this. So this becomes minus of 27.2 electron volt. Double of this, that's it. Okay. Here also double of that, minus 6.8 electron volt, minus 3 electron volt, and minus 1.7 electron volt. That's it. Okay. That's it. Considering that U at infinity is 0. My reference is at infinity. This is the normal reference. If nothing is specified, then we take our reference to be at infinity. Okay, we are assuming that when the electron and the nucleus, if they are infinitely separated, in that case the potential energy of the system is taken to be zero. It is assumed to be zero. That is our normal reference. Okay, if I change my reference, out of these three types of energies, which energy is going to change? For example, in the next problem here, what is kinetic energy, potential energy, and energy? And energy meaning thereby the total energy in second orbit of hydrogen. In second orbit, if potential energy in first orbit is assumed to be zero. Now, very interesting problem. This is my normal reference. Only under this reference, all this is applicable. If I change my reference, things are going to change. Which energy will change? Kinetic energy does not depend on reference. So kinetic energy will remain constant. This is not going to change no matter what is your reference. No matter what is your reference, kinetic energy is not going to change. Then what is going to change? What is going to change is potential energy. This is constant, but this is going to change. If this is going to change, then this also is going to change because total is kinetic plus potential. Okay, so these two energies will change. Now, what they will become? That will depend on our reference. Okay, so can you try to solve it on your own? The second problem where we are actually changing the reference. Okay, how will you do it? Okay, and if you think a little bit about it and try to recollect whatever you have learned till now, you will realize that this type of problem we have done already in the very beginning of this whole syllabus. Maybe in the chapter on potential energy, we have done this problem. How to calculate potential energy if the reference is changed. If you try to recollect that, okay, try to do that before we discuss. Of course, we are going to discuss now. Now we are going to discuss it. But before we discuss that, you try to do it on your own. Okay, pause the video, do it on your own. And now, assuming that you have done that, let's discuss it now. Okay, it's like this. Keep in mind, when you change the first of all, very first point, potential energy does not have any absolute value. Okay, think it this way. Okay, I'm going to give you one example here. Let's say that this is ground. Let's say that this is ground. Okay. And I have one object, let's say 1 kilogram object, 1 kilogram particle, and it is taken to some height. Let's say that it is taken to some height 5 meters above the ground. This is my particle. I bring my particle from ground to this height here. What will be its potential energy? We write it as mgh. This is 1 and this is 10 and this is 5. This is 50 joule. Now, is this absolute? It is not absolute. It is mgh only if I consider energy here to be zero. Only in that case. If I assume that energy on the surface is zero, only under that case energy at height h will be equal to mgh. If I change my reference, okay, let's say that energy here on the ground is 10 joule. It is not 0, but it is 10. Then what will happen? Everywhere 10 will be added. Okay, so energy here will become 10 plus mgh. Okay, this will be equal to 60 joule. If I ask you one more thing, what will be energy here? Okay, let's say this is 5 meter. If I ask you what is energy here at 3 meter, okay, this is 50 joule. What is energy here? this whole thing is 5 meter, this is let's say 3 meter. 3 meter. Energy here will be equal to 30 joule. Okay, same mgh. What will be energy here at a height of 3 meter here? This is 3 meter. Okay, energy here will be equal to 10 plus mgh of course. This is going to be equal to 40 joule. This is going to be equal to 40 joule. Now, let's understand few points. If I change my reference, here it was 0, I am making it 10. I am making it 10. Okay. So what will happen is 10 joules will get added everywhere. 10 joule will be added here and it becomes 10 joule. 10 joule will be added here also. This becomes 10 plus 30, 40. Everywhere, at every point, 10 joule will be added. It will be added. So this will become 10 plus 50, 60 joules. Okay, if I consider that it is not 10 joule here, but it is let's say it is minus 50 joule. For example, let's say that energy here is minus 50 joule. In that case, minus 50 will be added everywhere. 0 plus minus 50 plus minus 50. So becomes minus 50. 30 plus minus 50. It becomes minus 20 here. Okay, this will become minus 20. Minus 20 joule. Okay, this will be minus 50 plus this. Similarly, this also minus 50 plus this. Minus 50 gets added everywhere. This becomes 0. This becomes 0. Okay, now, so this is one method. If I change my reference, you add that much energy everywhere. Everywhere you do that. Look at the difference. No matter what is the reference. Okay, let me check if you are able to see it all right. Sometimes, well, this focus gets disturbed. No matter what is your reference, you see this interesting property. The difference of potential energy between two configurations, between 2 points, it remains constant. Between these 2 points, what is the difference? It is 20 joule. Difference here is 20 joule. And you see here also the difference is 20 joule. Okay. So potential energy of a given point changes, but potential energy difference, the difference in potential energy of 2 points, it does not change. It remains constant, no matter what is the reference. Okay. And this is the thing, this is the concept, property that we are going to apply to solve this problem here. What we are doing, okay? What we are doing, okay? We are doing it like this. This is the normal value, first of all. Okay, we are going to discuss how to solve it, how to get the answer. First, you forget about this question. This is the first step. First step is to forget about the problem. Okay, in most of the cases, this is a very good strategy. When you are faced with a difficulty, okay, the first step, and if you really want to solve that, okay, provided the first step is not in all the cases, but in most of the cases, it's a very good strategy. You forget about the difficulty. You forget about the difficulty. You will see that things slowly start to converge. Okay. Okay, here what we are going to do is we are not going to forget it, but what we are doing is forget this change in reference. You just write the normal value, taking your normal reference. You write all the value, total, kinetic and potential. Generally we start with total because we memorize this formula here. So we start with total, then we apply this relation to find kinetic and potential. Okay. So first you write all the energy taking the normal reference. Normal reference, that is U infinity is 0. Okay, you got all these values, we got it. Okay, now if I change my reference, remember this, very, very important. If I change my reference, then potential energy is going to change. direct impact, okay, is on potential energy. And now if this changes, then this also changes. Now how does it change? How does it change? What is the new reference? Potential energy in first orbit here, in the very first orbit is assumed to be 0. Generally what we do is, we take here, this is n is infinity, this is n is infinity, here I take u to be 0. Okay, but in this problem I am changing my reference. I am saying that assume this to be 0, so this u dash here is 0. U dash here is 0. Then what will be u? Okay, then what will be e dash? Okay, it is simply u dash plus k. K does not change, it remains constant. It does not depend on reference. Okay, so if I add this and this k, okay, it becomes plus 13.6 electron volt. And then remember, once you change your reference, this relation no longer holds. This relation holds only under this normal reference, when my reference is normal at infinity. The moment you change your reference, the moment you change it, then this will not hold. This will not hold. It is not going to be applied. Okay? So here we are discussing the method. Understand it. First you write the normal energy, taking your normal general reference, and then you make the change. Then what you are doing is, you are assuming this to be 0. Now to make this 0, understand it, to make this 0, how much do you need to add or subtract? Okay, you need to simply add 27.2 electron volt. If you do that, you get 0. Then you will add the same value everywhere, at every point. At every point this is going to be added. That way the difference between 2 points will remain constant. Okay, I have 3 and 5. I have one number is 5, another number is 3. Okay, what is the difference? What is the difference? It is 2. Now if I add same numbers, same quantity to both numbers, let's say let me add 100. Let me add 100 to both numbers. So 100 here also. So this becomes 105, this becomes 103. The difference remains same. The difference does not change. It's a very simple property. Same thing we are doing here. I am adding 27.2 electron volt everywhere. Whatever is required to make this 0, that much I am adding everywhere. Okay, do you see this? So here I will add plus 27.2 electron volt. Everywhere I am doing that. Okay, here also. Here also I am doing the same. Plus 27.2 electron volt, and here also plus 27.2 electron volt. Okay, you will get potential energy. This will be equal to 0.4, and then this is 619. I hope this is fine. Is that right? 19.4 or 20? Is it 20? 20.4 plus 20.4 electron volt. Okay, then what will be total? So this plus this. So 23.8 plus 23.8 electron volt. Do you see? Now here this becomes minus, okay, no. So plus 24.2 electron volt. 24.2, and when I add it with this here kinetic, okay, so this is my total energy. This is my total energy here. This becomes this plus this, okay. So 25.7 plus 25.7 electron volt. Okay. Do you understand this? Understand this? Now, what about this? What about this? This plus this. Okay, so this becomes 5. I just have to add it. No, first of all I need to subtract. So 2 minus 7 is 5, and then here I will get 6 minus 1 is 5, 25.5. 25.5. And then I need to add this here. I need to add these two to get total energy. So this becomes 5 and 3 and then 6, 26.35. It keeps on increasing. Energy keeps on increasing. Energy was minimum here. Here also it is minimum. Okay, it is ground state. Ground state will remain ground state, no matter what is your reference. Understand this? And not only that, you look at the difference in energy. What is the difference in energy here between 1 and 2? What is the difference here? Can you find out the difference? What is the difference of energy? 13.6 minus 3. This becomes 10.2 electron volt. And what is the difference here? What is the difference here? Difference between these two. Here also you should get the same answer, 10.2 electron volt. Okay, look at the difference here between 2 and 3. What is the difference here? So is it minus 1.9 or 1.9 electron volt? 1.9 electron volt. The difference, okay. What is the difference here? Here also you will get the same difference, 1.9 electron volt. Okay, the absolute values change. Okay, but the difference does not change. It remains constant. Okay, do you understand that? Do you understand this? Okay, good. Can you do the same, the next problem in the similar manner? Okay, energy in third orbit is assumed to be 0. Okay, I'm going to clean all this. Alright, note it down. Now, I'm changing my reference. Now, total energy I'm taking to be 0. Total energy. Okay, so let me write here. Total energy is 0. This was the original value, taking the normal reference. Kinetic energy is not going to change. It will remain constant. Now, if I take this to be 0, in where energy in third orbit or third state is 0, here I am taking this to be 0. Okay, then what do I do? What do I do to find energy in all the other states? Okay, so I need to find out how much has been added or subtracted. Okay, the normal energy under normal reference, energy in the third orbit here, third state, is minus 1.5. Okay, now this becomes 0. This becomes 0. That means plus 1.5 has been added. Okay, so plus 1.5 electron volt gets added everywhere. Plus 1.5 electron volt gets added everywhere. Okay, so if I do that, if I add 1.5 electron volt everywhere, then the energy in third state becomes 0, and that's what I want. That's exactly what I want. Okay, so here this becomes plus. Okay, I'm sure you can do that. You can do it faster than me. I'm sure about that. So this becomes 6 or 60. Okay, it is like 0.65. I hope that I'm doing it all right. What is this? This is the energy. Energy under the new reference. Energy under the new reference. This is 0. What about this? Minus 1.9 electron volt, I hope. Okay. Or, okay, let's say there is one other interesting method of doing that. Okay. What about this? This is minus of how much? 12.1 electron volt. Okay, got it? Got this answer? Okay. Now let's look at one very interesting thing here. Okay. What is the difference in energy between this and this? Between this and this, what is the difference? Between this and this, what is the difference? And between this and this, what is the difference? We calculated this, okay? This was, between this and this, it was 1.9 electron volt, okay? Between this and this is 13.6, minus 13.6, and this is like here, so this becomes 12.1. This becomes 12.1 electron volt. Okay, difference. The difference remains constant. Here, what is the difference here? 1.5 and 0.85, 0.65. Okay, I am not bothered about positive and negative. Okay, just the magnitude. We will see which one is higher and which one is lower. Now, if I take this to be 0, the energy is going to be constant. Now, energy of this is higher. As we go away, as we move away from the nucleus, as we go to the higher states have higher energy. Higher states have higher energy. Okay, energy of this is going to be higher. And what is the difference? What should be the difference? So if energy here is 0, energy here should be equal to plus 0.65 electron volt, because this is the difference. And you see this? Okay. Now energy this is 0, what will be energy here? This energy will be lower than this. This is a lower energy state, this is a higher energy state. This energy has to be lower from 0, less than 0. By what amount? 1.9. It becomes minus 1.9 electron volt. Okay. And here, see, this is 0 electron volt here. And what will be this value? This will become minus 12.1 electron volt. You see here also I got the same answer. Well, that's all. That's how you can do it. Now, once you know total, you can find this also. You can find this U dash also. U dash is going to be equal to E minus K. E minus K. Okay, this relation always holds. Total energy is kinetic plus potential. This is a general relation. Okay, it is always going to hold. Only the values will change. So this E dash, it is E dash here. E has changed. So this minus this, it is going to be equal to minus of how much? This, here this, minus this. So actually they are going to be added in magnitude. Okay, so 0.7 here and 25.7. Okay. Now here, this and this, they are actually going to be subtracted in magnitude. It will be positive here. Will it be will it be how much? 1.5? This? No, I have to subtract it. This minus this, so the magnitude is going to be added. Okay. Magnitudes are going to be added. 9 and 4 is 3. And 3 and 1, 4 and 1, 5. It's like this, minus 5.3. This is 0. This, minus 1.5 electron volt. Here, this minus this. This thing minus this. Okay. So minus 0.2 electron volt. Okay. And now, one other important thing. Okay, I am showing you different pictures. Okay, I am showing you the same thing from different angles. Okay, we are having this 360-degree view. Okay, panorama view of the whole thing. The same structure I am going to analyze from different angles. Now, what we did to change the reference, I added this thing plus 1.5. Kinetic energy is constant. Understand this. Kinetic energy is constant. If I add something into potential energy, the same thing is going to be added in total also. Okay. So if something is obtained after adding something to the total, then that something needs to be added in the potential as well. Do you follow the logic? Try to listen to that again. Okay. So I am adding plus 1.5 here. So I should add plus 1.5 everywhere here. You see, if I do that, what do I get? I get this plus 1.5 electron volt. If I do that, I get this. You see directly plus 1.5 electron volt. If I add both, I will get this value here and plus 1.5 electron volt. If I do that, I am going to get this value here. Are you able to follow all of this? Okay. Do not make it difficult. Okay. Try to understand it in a normal, simple, normal way. Okay. Do not look for any formulas or any relations. Okay. There are formulas for everything. Keep that in mind. You open a book, you will find thousands of formulas. But always keep in mind, are you really going to remember all those formulas? Do you really think you can do that? Okay? Think about it. Before remembering any new formula, ask this question, am I going to need it, first of all? And second question, if I remember it now, what are the chances I will be able to retain it by the time I am really going to need it? Can I do that? Okay? Do I have such a strong recollection that I remember a formula now? What are the chances that I am going to remember it the same way in examination hall as well? If you have any doubt, then you start looking for the alternatives to formula. If you want to survive, of course. Okay? Okay, so we did it, the second one also we did it. Now the third one, okay, the third question, okay, let's try to answer this. Third one. In case of helium, now the atom has changed. It's an ion, okay, ion atom, okay, that's fine. Okay, no big deal. It should be one electron system, that's it. Atom or ion, one electron system. If it is a one electron system, I can apply Bohr's law. Okay, I can apply. The Bohr's theory is applicable only and only for one electron system. That is hydrogen-like atoms. Hydrogen plus hydrogen-like. What is the meaning of hydrogen-like? It means hydrogen-like hydrogen, okay? One electron system, that's it. One single electron. One electron. Helium positive ion, helium plus one electron. So what will be energy? First of all, what is energy? Energy is equal to minus of 13.6, okay? Z square over N square, okay? For helium, what is Z? Z is 2. Atomic number. Hydrogen, helium, lithium and all that. You know this periodic table. So helium is Z2. Okay. So now what will be, let's write the energy. Okay. And some very important terms we are going to use and define here. Okay. So you have to do it very, very carefully. Very carefully. The second orbit here. Okay. Second, third and all that. Second, this is third. Okay, and let's say that this is infinity. This is infinity. Okay, this is n is equal to 1. This is n is equal to 2. This is n is 3. This is n is infinity. Okay. What is energy? Okay. This is Z is equal to 2. Okay, so energy here E1 is going to be equal to minus of 13.6 into 2 square over 1 square. Okay, so 4, it gets multiplied by 4 it becomes 54.4 minus of 54.4 electron volt. What is this? This is energy of helium in ground state. This is ground state. This is ground state. This is first excited state. First excited state. This is second excited state. This is ground state. Second state here. What is energy? Minus 13.6 and 2 square over 2 square. It is minus 13.6 electron volt. Energy in second state, that is second orbit. Okay. Energy in the third state here, minus of 13.6 and 2 square over 3 square. Okay, so it's like this, minus of 13.6 times 4 over 9. Okay, this will be approximately minus 1.5 times 4. Okay, I am writing the approximate answers. Okay, do not make much fuss about it. Because I don't. Okay, so this is a minus 6 electron volt. Okay, what are these? Are energies in different states. What I want to find? I want to find this energy required. How much energy is required? Okay, that means okay, let's understand the problem first. From ground to second excited state. From ground to second excited state. Okay, that means my atom is in ground state. What is the meaning of this statement? That atom is in the ground state. That means the electron is in the ground state, first state. First state. My electron is here. My electron is here. I want to send my electron from ground state to second excited state. I want to send my electron from here to here. Energy has increased. When the state increases, higher states are also higher energy states. Direct correlation. Higher states are also the higher energy states. Okay, I want to send my electron from this state here to this state here. Energy has increased. So who will supply that energy? So I have to supply that. I want to send my electron. I want to move the electron from here to here. I need to supply the energy. How much energy? Equal to the difference. So equal to whatever is the difference in energy. Okay. So if I want it, okay. So if I want my electron to go from ground to zero, I need to supply energy. Okay. This delta E will be equal to final energy minus initial energy. That means energy in second excited state. This is the second excited state. Okay. So energy here will be E3. It is E3 minus E1. Okay. E3 is minus 6 minus 54.4. This will be equal to 40, how much? 48. This is plus 48.4 electron volt. Okay. This is how much energy I need to supply. Okay. How do we supply? Do I hit the atom? How do you think you can supply energy to an atom? I can supply energy to this gross object, this bulk object. I can hit it with hammer. I can put it on stove. I can place it under sun. It can absorb energy. I want to supply energy to an atom. Can you imagine? How do we supply? Here also we do the same thing. Okay, we cannot really pick up one atom and then hold it in and somehow and then supply the. What we do is we heat it. Okay, we give it some heat. We irradiate it, like I bombard photons. I shine light. I can shine X-ray, lasers, whatever. Okay, then that's how energy is transferred. Okay. Now, so this much energy. What is happening in this process? In this process, electron goes from ground state to some higher state. Some energy is required. This is this required energy, this energy that is required for this transition, okay, this is known as transition. Transition means changing the state. An electron goes from lower energy state to higher energy state. It's a transition. Transition. You have to supply energy in form of photons. So photon will hit the atom. The electron is going to absorb that energy and it is going to jump there in that state. Okay. This energy is known as excitation energy. Excitation energy. All of these are different terms. Excitation energy, ground state, excited state. Excitation energy, energy required to excite an electron from ground state to one of those excited states. Okay, this is the first excited state. Okay, here this transition is happening from ground state to second excited state. The required energy is known as second excitation energy. This is second excitation energy. Okay, that means from ground state, from ground to n is equal to 3. From ground to second excited state. From ground to second excited state. This is n is equal to 3. This will be known as second excitation energy. Okay. Now what will be this energy? I want to send my electron from ground state to this first state. Second state. Ground state to second state. Second state is first excited state. So energy required, whatever energy I need to supply, that energy will be known as first excitation energy. Okay, that is from ground to first excited state. Do you understand this? First excited state means n is equal to 2, second state. Okay, do you think you can understand this? You can remember this? I am not writing definition. There are definitions, of course. The way we have formulas for everything, the same way we have definitions for everything. Okay? But then again, how many definitions do you think you can remember? Okay? You check yourself under this criteria, whether you are going to remember, whether you are going to be able to remember and recollect, if required, all those definitions. Okay? It's better to understand it through problems. Okay? It's a very efficient way of doing that. Okay? That's what is my experience, okay, in teaching. Okay? Do not run after the definitions and formulas and all that. Try to understand it in simple ways. Okay? You try to make it as simple as possible, because things are simple. Okay? Academicians like to complicate the thing, okay, to increase their worth. Okay, but it is of course nonsensical. Okay, try to understand it the simplest way possible. Okay, that's what it is. Now there is one other interesting thing, very interesting thing. Okay, very interesting thing is like this. Okay, there is one other term which is known as excitation potential. Excitation potential. Excitation potential. Okay, before we define it or even understand it, okay, let me ask you one question. I think we have some time. You can continue. Okay. Well, let me ask this question. Motion of charge under potential difference. Under potential difference. Okay. I don't think we are going to complete this. Let's do this in the next class. Okay. These two problems we are going to do in the next class. Okay. So I'm going to clean this anyway. Let's complete this only. Let's complete this one. These two problems in the next class we are going to do. Okay. All right. Now it's like this. So this you understand? Excitation energy. First excitation energy. Second excitation energy. Okay. Now, excitation potential. I have this electric field. This is my electric field. Let's say that this is my electric field. Electric field. Okay. I have one electron here. One electron. I release the electron in this electric field, uniform electric field, or whatever it is. I release the electron from rest. From rest. In what direction it is going to move? One electron. It is going to move in this direction because the force will act opposite to the field. Now, what is the relation between field and potential? Along the field, potential decreases. Opposite to field, it increases. Okay, let's say that potential here is 10 volt. Let's say potential here is 10 volt. Potential here, will it be more than 10? Less than 10. Opposite to field, potential increases. Let's say that potential here, this is plus 10 volt, this is plus 25 volt. Okay, so when I release the electron, it starts going from lower to higher potential. This is the spontaneous natural motion of electron. Any negative charge, it goes from lower to higher potential under the spontaneous motion. If there are no external forces in that case, if it is simply released, okay, then it will go from lower to higher potential. Now, in that process, you see the force keeps on acting in the direction, it keeps on gaining kinetic energy. If the kinetic here is 0 electron volt, what is the kinetic energy here? By the time it reaches here, it will have some velocity. It is going to have some velocity. Here it is released from rest. Okay, here velocity is 0. So kinetic energy is 0. What will be kinetic energy here? Okay, so this delta K is equal to Q times of delta V. It gains or loses. So under the spontaneous motion, it gains kinetic energy. And that gain will be equal to the potential, it will depend on potential difference. So potential difference is 15 volt. Okay, so the kinetic energy gain will be 15 electron volt. Okay, it's like this. This is E and this is 15 volt. Okay, this becomes 15 electron volt. Okay, this E and V, it becomes electron volt. Okay, a very interesting way of doing these things. Okay, we have the, okay, I hope that you are able to follow all this. Okay, now, so through what potential difference through what potential difference an electron should move to gain this much kinetic energy? This much energy. What is this energy? This is the energy that is required to move the electron from ground state to this state. This is my second excitation energy. If my second excitation energy is 48.4 electron volt, and then if I ask you this question, through what potential difference an electron should move to acquire, to gain this much energy, it will be equal to 48.4 volt. That's it. Okay, so this will be my second excitation potential. This will be second excitation potential. It will be simply equal to 48.4 volt. That's it. Okay, so if my second excitation energy is 48.4 electron volt, then second excitation potential will be 48.4 volt, and that's it. Okay, what will be first excitation energy? First excitation energy from here to here. Or if I ask you another question, what is first excitation potential? Let me ask this. Let me ask this question. What is first excitation potential? Okay, what is first excitation energy? Let me calculate this. Okay, this is delta E. Let's say delta E will be equal to E2 minus E1. Okay, so this will be equal to E2 minus 13.6 minus 54.4. Okay, electron volt. All of that in electron volt. It is going to be equal to plus. Okay, this is the 8 and 0 and 4. Makes sense? No, never. It cannot. Does that make sense? 8 and 6 is 14, 3 and 1 4 and 4 5. Okay. So plus 40.8. What is this? It is electron volt. This is first excitation energy. Okay. If I ask you what is first excitation potential? First excitation potential. It is simply equal to 40.8 volt, and that's it. That means if I move an electron, or if we accelerate an electron through a potential difference of 40.8 volt, it is going to gain kinetic energy of 40.8 electron volt, and that's it. Okay, that connection you have to understand properly. Okay, if you have any difficulty, then remember it. If you have any difficulty establishing and seeing through this connection, for the time being, you can remember it, memorize it. There are few things which do not really strike at the first moment, but with time, you will be able to see the connection, okay, very clearly. Okay, do you understand this? So this is about excitation energy and excitation potential. Okay, now let's complete this thing. Okay, we are going to complete this thing. Now the second problem, ground state to infinity. Ground state to infinity. What is the meaning of infinity? The meaning of infinity is the electron becomes free. The meaning of infinity is that electron becomes free, energies become zero, the components are separated, now there is no more interaction between them, no force between them. Okay, understand? Potential energy has to do with interaction. No force, no interaction, no potential energy. Okay, at infinity, this is the meaning of infinity. Now the electron becomes free from the bondage of nucleus. Free from the influence of nucleus, okay, in a more technical sense. So I want to send my electron from this ground state to this, I want this to become free. Now when it becomes free, what it becomes? It becomes an ion. From a neutral atom, if one electron goes out forever, okay, it becomes an ion. So this is known as ionization energy. Okay, so here this is known as ionization energy. Okay, energy required to send or move electron from ground state to n is equal to infinity. That means it becomes free. Or you can say that to detach the electron permanently from the atom, to remove the electron. Okay, it is known as ionization energy. Okay, so what it will be equal to? This is delta E. It will be equal to E infinity minus E1. That's it. Ionization, very important. To move electron from ground state. It's very important term. You see, electron can be in any state. It's not that electron is always in the ground state. It keeps on changing. Keeps on changing. That's how matter radiates. The electrons keep on jumping between states. Okay, you see, it is because, for the simple reason, atoms are never at rest. So in a sample of atom, they are always going to be colliding with each other. Always, continuous process, 24 hours a day. Every time, they are never at rest. They are never ever at rest. And if you give it a little more thought, nothing in universe is ever at rest. Everything is moving, and that too continuously. Continuous, every moment. Not for a moment anything is at rest. Because for universe, for nature, rest is death. Okay, motion is life. Life is motion. Okay? This whole universe is a living, a live thing. It's pulsating with life all the time. Pulsating life. Everything is in perpetual motion, everything. So atoms keep on moving, colliding and all that. During collision, they exchange energy. Using that energy, electrons, okay, they jump to the higher states. After some time, they come back. Okay, they absorb radiation, they emit radiation. All these things happen perpetually. Okay, all the time. All the time it's happening. Okay. You think about it or you don't think about it, they don't bother. They keep on playing this beautiful game all the time. Okay. Okay. So this is it. Okay. So this is about, so from ground state. Okay. Not from this state. Not from this state. From ground state. I want to remove one electron from the ground state. That energy required is known as ionization energy. Okay. I'm not defining it. I'm not writing it down. I'm not writing it down. I'm just defining it through this problem. Okay. And you have to understand it. Once you understand it, then definitions become superfluous. And they will not be required. Then you can define it in your own language. Okay, I don't really have to tell it to you. You can do it on your own. So this becomes 0 minus of 54.4 electron volt. It becomes plus 54.4 electron volt. This much energy is needed. This much energy is needed to ionize the atom. And whenever we say ionization, that means from ground state, from the lowest possible state. From the lowest possible state in terms of energy. Okay, this much energy. And then what will be, you see, answer this directly. Ionization potential. Ionization potential. Okay. If ionization energy is 54.4 electron volt, what will be ionization potential? It will be same 54.4 volt, and that's it. It has the same meaning, the same thing that we discussed for excitation potential. Exactly the same meaning is attached here as well. Okay, we got this point. Now, one new term. Each problem related with one term here. Now, what is this? What is the difference between this and the last question? B. N is equal to 1 to n is equal to infinity. Now, this is known as ionization energy. Ionization energy. And here, you see the same thing is happening. I am taking out the electron, that's it. In first case here, I am taking out the electron, I am removing the electron from ground state, from n is equal to 1. That energy is known as ionization energy. Okay. Here also I am doing the same thing, but now I am removing the electron from this second state, Essentially the same process, but different terms are used. Different terms. The term that we use here is not ionization. Ionization is very fixed meaning, from ground to infinity. I want to remove the electron from ground state. I want to separate it from the atom. That is ionization energy. Here also I am separating, I am doing the same thing, but I am doing it from n is equal to 2, from this state, not from this state. Okay, the process is essentially the same. This is the only difference. This is the only difference. In ionization, I am removing the electron from the ground state, and in this process I am doing it from the second state, n is equal to 2. This is known as binding energy. Binding energy of second state. Second state. Okay, so this delta E is equal to E infinity minus E2. 0 minus of 13.6 electron volt, it becomes plus 13.6 electron volt. You understand this? I'm not going to say anything more. Okay, I'm sure that you must have got the point. Okay, so binding energy from the first state is same as ionization energy. Okay, but generally we use the different terms. Ionization from ground state, from any other state, it is binding energy. Excitation, again, let's revise things. Excitation from ground to any other. From ground to any other. Okay. What about any other to any other? Okay. For example, from this state to this state, what do I call it? This is not excitation. Excitation is from ground to this. From ground to this. This is excitation energy. From this to this, I need some energy. But that energy is not called excitation energy. It has no name as such. Okay, I will simply ask you to find what is energy required to move an electron from first excited state to the second excited state, or from second state to the third state. I will not give it some name. There is no name for that. It's a general term. Okay, so I will simply ask you to find energy. That's it. How much energy is required to move an electron from second to third state, from second to fourth state, and all that. Okay, so no special term is defined for that. Okay, so that's it about it. Next class we are going to continue with this. Those two problems we will do plus few more. Okay.